Let me go live first. Okay, so welcome everybody. It's a great pleasure to introduce Ankush Goswami. He finished his PhD with Krishna Aladi, I think 3 years ago, in
2019, yeah.
from University of Florida, and then he spent some postdoc here with Peter Paule at Linz, and now he is currently a postdoc in IIT Gandhinagar, and will soon be. I think he's still deciding where he's going to go afterwards. But we are very happy to introduce him. He's a very bright person who has thankfully come back to India and will contribute here. His topic is partial theta series with periodic coefficients and quantum modular forms. Ankush.
Thanks, Gaurav, for the introduction, and thanks all for being here. I'd also like to thank Gaurav and Atul for inviting me to speak. So today I'll be speaking on this topic called partial theta series with periodic coefficients and quantum modular forms. Before I get into my slide, let me tell you that partial theta series first appeared in Euler's work in connection to partitions. And Euler actually showed that if you take the product of 1 minus q to the power of n, as n runs from 1 to infinity, which basically is the reciprocal of the partition generating function, then Euler showed that this infinite product is equals to a theta series, where the exponents of q in the theta series are some interesting numbers, which are called pentagonal numbers. And so this result of Euler came to be known as Euler's pentagonal number theorem. Later, Jacobi did a more systematic study of of theta series, and he actually used elliptic functions to study the theory of theta series or theta functions. And he actually showed that theta series or theta function satisfies some nice transformation properties. And yeah, and because of the transformation properties that theta functions or theta series satisfies, we find several applications of this series in different areas of math as well as physics. So I will show you some applications of this series later in my slides. Concerning partial theta series, I don't know where this series first appeared or in whose work, but in Ramanujan's Lost Notebook, you find lots of different identities of Ramanujan, which Ramanujan writes without proof, and where you find this partial theta series. So unlike the theory of theta series, where you have very nice transformation properties of the series, we do not have a good understanding of partial theta series. And it is the goal of this talk to actually show you some interesting transformations or properties of partial theta series with periodic coefficients and their connections to quantum modular forms, which I will describe later in my slides. So let me begin with the outline of my talk for today. So I have two main goals in my talk. So the first goal is to discuss a general result on quantum modularity of certain partial theta series with periodic coefficients. And as a corollary of our first goal, we will show the quantum modularity of the Concevi-Zagier strain series. So this is a particular kind of series, hypergeometric series, which I will describe later in my slides. And this series is actually associated to a family of torus knots. So this family of torus knots, T3, 2 to the power of small t, where small t is bigger than or equals to 2. And this generalizes a result of Zagier in 2001. And then we also show quantum modularity of Rogers' false theta function, which is an important function in Q series and partitions as well. So this work is basically based on my recent joint work with Robert Osborne at University College Dublin, and the title of this work is Quantum Modularity of Partial Theta Series with Periodic Coefficients, which appeared recently. Okay, so let me start off with the definition of a theta and a partial theta series. So if Q is any complex number inside the unit disk and X is any non-zero complex number, then you consider this bilateral series. So this is the series running over the variable n from minus infinity to plus infinity of x to the power n times q to the power n squared. Then such a series will be called a theta series, or you can consider a specialization or a generalization of this series, which will also be called a theta series. Similarly, a partial theta series is defined in a similar way, except that now the variable n runs from 0 to infinity instead of running from minus infinity to plus infinity. And you can again consider a specialization or a generalization of this series, and this will be called a partial theta series. Okay, so we'll assume throughout that Q is this complex number, which is given by e to the power 2 pi I z, where z is in this set, the set of all complex numbers with positive imaginary part. And this is called the complex upper half plane. And since z has imaginary part positive, we see that the absolute value of Q is strictly less than 1. Some examples. So if you consider this, the first series with x equals to 1, which is denoted by theta sub 0 of z, then this is defined to be the sum running over all integers n of q to the power of n squared. So this is an example of a theta series. And then if you consider the left hand side, which is 1/2 of theta sub 0 of z plus 1, then this becomes a partial theta series where the sum runs from n equals 0 to infinity of q to the power n squared. And this is basically a partial theta series. And as you can see in this case, the partial theta series can be expressed in terms of the theta series, but this is not the case all the time, as we will see some examples later. Now the question is, why do we care about theta series? So I already told you that theta series satisfies some nice transformation properties, and it is because of the transformation properties that theta series satisfy. They find lots of applications in different areas of math as well as physics. So let me just discuss a few examples in mathematics, in particular number theory and Q series and partitions. So if you consider this function, which is called the Dedekind eta function, eta of z, which is defined to be q to the power 1 over 24 times the product n equals 1 to infinity, 1 minus q to the power n, then this function plays a very important role in Q series and partitions. In fact, if you just take the reciprocal of this function, then this gives you essentially the generating function for partitions. And this is an example of a theta series. And since the theta series and I actually write down here that this function eta of z is exactly given by this theta series. So this actually looks like a partial theta series because the sum simply runs over all non-negative integer. But if you get rid of this Kronecker symbol, so this 12 divided by k within parentheses is the Kronecker symbol. So if you get rid of this Kronecker symbol, you actually get a theta series. So this actually looks like a partial theta series, but this is a theta series. And this follows from Euler's pentagonal number theorem. Okay, so that. And then Riemann also used theta series to find the functional equation of the Riemann zeta function. And then theta series are also used in finding the number of representation of numbers by sums of certain numbers of squares. A famous example is the Jacobi's four-square theorem, which gives you a formula for the number of representations of number as sums of four squares. Okay, so that. And then, yeah, about the Dedekind eta function, because you can write the function eta of z in terms of this theta series, and since theta series has transformations, so you get transformations for the Dedekind eta function. And so these transformations are actually used in different areas. For example, to understand the asymptotic behavior of the number of partitions of a number P of n, you use this transformation for the Dedekind eta function. So yeah. And then, you know, in 1973, Shimura generalized this idea of theta series, and he actually generalized it to objects which are called half integrated with modular forms, of which theta series are first examples. Theta series are first examples. And he actually introduced them in order to find a connection between half integrated with modular forms and integrated with modular forms via the theory of L functions. So let me define here what are half integrated with modular forms. And in order to define these, I need to introduce a few notations here. And in the process, after I define half integrated with modular forms, we can also see the definition of integrated with modular forms. So this basically stands for the extended Jacobi symbol, which is basically the Jacobi symbol extended to all integers in a certain way. Chi is basically a Dirichlet character, mod 4n, where n is a positive integer. Epsilon sub d is 1 or I, according as d is congruent to 1 or 3 mod 4. And gamma sub 0 of n is this congruent subgroup, or this is a subgroup of SL2Z, where this lower left entry C is a multiple of n. And then one can define a half integral weight modular form, which is a function defined in the upper half plane. And it is defined to be a holomorphic modular form of weight lambda plus 1/2, where lambda can be any integer, and Levin type is chi over gamma sub 0 4n if it satisfies the two conditions. The first condition is it should be holomorphic in the upper half plane H, and it should be holomorphic on the cusps of gamma sub 0 4n. Now, what do I mean by the cusps of gamma sub 0 4n? So, in order to define a modular form, what you need to do is you need to look at the action of a group in the upper half plane. In this case, the group is basically gamma sub 0 4n, and gamma sub 0 4n x in the upper half plane H by fractional linear transformation. And you'd like to see what happens when gamma sub 0 4n x in the set of rational numbers Q. And the set of equivalence classes that you get under the action of gamma sub 0 4n on Q will actually give you the cusps of gamma sub 0 4n. So yeah. So basically, the first condition tells you that F should be holomorphic in the upper half plane, and it should be holomorphic in those equivalence classes where gamma sub 0 4n x are the set of rational numbers. And the second condition tells you that the function f satisfies this transformation property, that if you take f of az plus b divided by cz plus d, then in the right hand side you have this thing, you have chi of d times this quantity, which is called a multiplier, which depends on the matrix that you are choosing. So in this case, the matrix is A, B, C, D inside gamma sub 0 4n. And yeah, and then you have cz plus d to the power of lambda plus 1/2 times f of z. So as you can see, the weight, which is lambda plus 1/2 here, this appears as the exponent of cz plus d. And then this quantity is the multiplier, and this corresponds to the value of the character pi. And this transformation should hold true for all matrices A, B, C, D inside gamma sub 0 4n, and for all points z in the upper half plane. So if these two conditions are satisfied for this function f, then we say that f is a holomorphic modular form of weight lambda plus 1/2 and Levin type plus chi of gamma sub 0 4n. And you can similarly define a modular form of integral weight. That means if you replace lambda plus 1/2 by an integer, then you can define a holomorphic modular form of weight, let's say k, and Levin type plus chi over gamma sub 0 4n if it is holomorphic in the upper half plane and on the cusps of gamma sub 0 4n. So in this case, like for the integer weight case, you don't need gamma sub 0 4n. Only when the weight is half integral, you need gamma sub 0 4n. For an integral weight, you can actually define it over gamma sub 0 of n instead of a 4n here. And then the second property is about it satisfies the similar transformation property, except that you don't have these multipliers. So you don't have these multipliers, the extended Jacobi symbol, and then you don't have this epsilon sub t. So if the function f of an integral with k and Levin type plus chi over gamma sub 0 of n satisfies these two conditions, then it is called a holomorphic modular form of integral weight. Okay. And then if the function f vanishes at all the cusps of gamma sub 0 4n, then it is called a cusp form. And then we denote the space of modular forms of weight lambda plus 1/2 and Levin type plus chi over gamma sub 0 4n by this, by m sub lambda plus 1/2 of gamma sub 0 4n comma chi, and the corresponding space of cusp forms is denoted by s sub lambda plus 1/2 of gamma sub 0 4n comma chi. And then I will just show you a few examples of theta series, which appeared in Shimura's paper as well. And these are theta series involving certain characters. So let me just define this theta series first. So suppose psi is a primitive Dirichlet character with conductor R psi. And then you define this theta series, theta of z comma nu comma psi, which is defined to be this bilateral sum over all n going from -infinity to +infinity of n to the power of nu times psi of n times q to the power of n square, where n can be either where nu can be either 0 or 1. Then Shimura showed that this theta series is a modular form precisely in these two cases. When nu is 0 and when psi is even, the corresponding theta series that you get is a modular form of weight 1/2 in this congruent subgroup with the character psi. And when psi is odd, and nu is 1. Corresponding theta series, theta of z comma 1 comma psi, is a cusp form with 3/2 in this congruent subgroup with this character, where chi sub -4 is the non-trivial Dirichlet character modulo 4. Now, one can ask the following question by looking at this result of Shimura. So what happens in the first case when you replace the character psi by an odd character? And what happens in the second case when you replace the odd character by an even character? That means what happens to theta of z comma 0 comma psi when psi is odd, and what happens to this theta function theta of z comma 1 comma psi when psi is even. And to answer this question, we need to introduce some new objects, another new object, which is called a quantum modular form, which was introduced by Zagier in 2010. And we will see very shortly that this theta series that you have in question 1 are actual examples of quantum modular forms, but will prove a more general result from which we'll get the answer to question 1. Okay, so let me now define what are quantum modular forms. So quantum modular forms basically were introduced by Zagier in 2010, and it is defined as follows. So a quantum modular form of weight k, which could either be an integer or half an integer, is a function g defined from the set of rational numbers to the set of complex numbers, for which this function r sub gamma, which is defined from q minus gamma inverse I infinity, this set, to the set of complex numbers, which is given by this difference g alpha minus c alpha plus d to the power of minus k times g of a alpha plus b divided by c alpha plus d, and this difference is denoted by r sub gamma of alpha. So this difference should extend as a real analytic function on the projective real line, excluding a finite set of points s sub gamma for each gamma in SLZ. So this is basically the definition of a quantum modular form. And if you want to draw a parallel with the definition of modular form, so in the case for a modular form, so there are two important differences. So the first is a modular form is defined in the upper half plane, but a quantum modular form is defined on the set of rational numbers. A modular form can also be defined on the set of rational numbers wherever it is defined. But a quantum modular form is defined only on the set of rational numbers. The second thing is, for a modular form, this difference is 0. But for a quantum modular form, this difference is not 0. And this difference is sometimes called obstruction to modularity. That means this difference is not 0, but it could be a paramorphic function sometimes, it could be a real analytic function sometimes, it depends on the problem. But according to the definition that Zagier gave, this difference should be a real analytic function, or this difference should be rather nice. That's what Zagier states in his definition. This difference should be a nice function, and nice here could mean a real analytic function, a continuous function, a holomorphic function, and so on. Yeah, so that. And then people have modified the definition of Zagier to actually by actually restricting the domain of this function r sub gamma to appropriate subsets of a set of rational numbers, and they have also allowed certain multiplier systems and transformations on subgroups of SLs. So basically that, and then there are several implications of quantum modular forms in physics, in knot theory, and in several other places. So I'm no expert in any of these areas, but I will still mention where this quantum modular forms find applications. So they find applications in mass forms, in supersymmetric quantum field theory, in topological invariance for Plum 3 manifolds, in combinatorics, in unified Witten-Reshetikhin Duraev invariance. Probably in this field of unified Witten-Reshetikhin Duraev invariance, Zagier actually found, I mean, in connection to this area, Zagier actually studied some function which had actually quantum modular behavior. And that's where that's how he actually defined he actually gave the definition of quantum modular. Then they have applications in L functions and knot theory. Okay, so let me now tell you the motivation of our problem. So the motivation came from the study of this function by Zagier. And this function satisfies a really strange identity, which I'm going to show now. So this function f of t is defined to be this infinite series over all non-negative integers n, of 1 minus q times 1 minus q square all the way up to 1 minus q to the power of n. And Zagier showed that this function satisfies this, I should not say an identity, but this type of a thing, which is called a strange identity, because on the left hand side you have the function f of q, in the right hand side you have a partial theta series, and then in between you have this equality within quotes. So what this means is as follows. So the left hand side, which is f of q, so this is the function which does not converge anywhere inside or outside unit disk, but it is defined when q is a root of unity, in which case this sum reduces to a finite sum. The right hand side is the partial theta series, and this actually converges when q is inside the unit disk. So what this equality within quotes means is, if you take the value, if q is basically a root of unity, then f of q has a well-defined meaning because it's a finite sum, so it's a finite value. And when you take the radial limit of the right hand side, as q approaches that particular root of unity, it has a well-defined value as well. And in that case, the two become equal. That is the meaning of this identity. So as I said, the right hand side is a partial theta series, and it does not have any modular properties. And Zagier actually showed that the right hand side has quantum modular properties, from which he actually deduced the quantum modular properties of the function f of q. And that's basically what I'm going to just tell you now, just the main ideas of Zagier's proof of the quantum modularity of the function f of q. So what Zagier did was to show that the right-hand side can be viewed as the Eichler integral of the Dedekind function. So I will show you later in my slide how a particular Eichler integral looks like. But basically, this is a complex integral involving. So this is basically a path integral involving complex functions. So what Zagier did was to show that the right-hand side can be viewed as the Eichler integral of the Dedekind eta function, eta of z. And then he showed that this Eichler integral has quantum modular properties, and these properties are basically coming from the modular properties of the eta function. And then using the strange identity, he actually showed that the quantum modular properties of the right-hand side are actually transferred to the left-hand side by the function f of q. That actually shows that this function f of q is a quantum modular form. And using this idea, we actually got the motivation. We actually got the motivation to do our problem, because what Zagier is trying to do is he's trying to find the quantum modular properties of the right-hand side, which is a partial theta series. And then he's transferring the properties of the right-hand side to the left-hand side via the strange identity. So what we did in our case was to consider more general partial theta series and to study quantum modular behavior of this partial theta series, which is something that I'm going to describe very soon. But yeah, the motivation came from studying the strange identity of Zagier. Okay, so now an observation. So let us go back to question 1. So in question 1, I asked what are the objects theta of z comma 0 comma psi when psi is odd, and what is theta of z comma 1 comma psi when psi is even. So when psi is even, the first one gives you a modular form of weight 1/2, and when psi is odd, the second one gives you a modular form of weight 3/2 by the result of Shimura. This is what you get. And now I can, so if you take this example, where in this case you can just, so if you get rid of the sign, so this basically sine of n is the sine function, which is defined to be +1 when n is a positive integer, and -1 when n is a negative integer, and it is 0 when n is equals to 0. So if you consider this function, which is the sum running over all n, from -infinity to +infinity, but only in certain arithmetic progression of sine of n times q to the power of n squared by 2n, then this corresponds to a psi function being odd. And this is an example of a false theta function. And it turns out that this is an example of a quantum modular form of weight 1/2. And then in the second case, as shown by Zagier, if you consider this function, this partial theta series, where the sum now runs from 0 to infinity of n times this Kronecker symbol times q to the power of n squared minus 1 divided by 24, where this Kronecker symbol is an even function now. So this is an example of quantum modular form of weight 3/2, which was shown by Zagier, and something that we already seen in the last slide. So basically, now I'm going to describe the general result from which the quantum modularity of these two, as well as the quantum modularity of the functions that you have in question 1 follows. So for that, I will actually define partial theta series with periodic coefficients. So let f be a function which is defined on the set of integers to the set of complex numbers. And suppose this is a periodic function with period m bigger than or equals to 2 with a certain support set which depends on some positive integer k sub naught. And suppose you consider this set m sub f of k naught, which is a non-empty subset inside the support of the function f. And then you consider the two partial theta series. One is small theta sub f of z, which is the sum running from 0 to infinity of f of n times q to the power of n squared divided by 2m. And the other is capital theta sub m, capital theta sub f of z, which is defined to be the sum running over all non-negative integers of n times f of n times q to the power of n squared divided by 2m. Then, and also you define this subgroup. This is a subgroup inside gamma sub 0 of n, which consists of all those matrices in gamma sub 0 of n where the diagonal entries are congruent to 1 mod n. And then you define this congruent subgroup gamma sub m, which is defined to be gamma sub 1 of 2m when m is even, and it is defined to be a subgroup inside gamma sub 1 of 2m with a condition that this entry b should be even when m is odd. So yeah, and then you define a subset of a subset of rational numbers, which is defined to be the set of all rational numbers where alpha is equivalent, where alpha is gamma m equivalent to I infinity under this condition, and alpha is gamma m equivalent to 0 or I infinity otherwise. So you define this set. And then if you take any gamma in gamma sub m, then it follows that if f is an even function, then small theta sub f of gamma z satisfies this transformation with a 1/2 appearing as the exponent of cz plus d. That tells you that it is a half integral with Theta series type of thing. And then when f is odd, capital theta sub f of gamma z satisfies this transformation where you have a 3/2 in the exponent of cz plus d, telling you that this is a Theta series of with 3/2. And to obtain these transformations, what you have to do is you have to first show that both this partial theta series, small theta sub f and capital theta sub f, are linear combinations of generalized theta series that Shimura considered in this paper. And then you use the transformation properties of generalized theta series that Shimura obtained in his paper to find transformation properties for, this transformation properties for the small theta f z function and the capital theta sub f z function. So basically that is the idea. Okay, so now the question is what happens? So we already saw in the previous slide that when f is even, small theta sub f of z satisfies the transformation property, and similarly when f is odd, capital theta sub f of z satisfies the transformation property. So the question here is what happens when f is odd, and in here what happens when f is even. So if we can answer this question, this will answer the question that we posed as question 1. So that is basically what we are trying to do now. So you consider any fixed k sub naught, which is inside 1 and 2m, and then you consider the set S of k naught, which is the set of all integers in between 1 and m by 2, such that this congruence condition is satisfied. And this congruence condition, this set is actually defined in a natural way in the sense that you have to use Shimura's transformation. So this set is accordingly defined. And then you consider any non-empty subset inside this set S of k naught. You consider this set m sub f of k naught, which is any non-empty set inside this S of k naught. And then you define or you consider those functions f which satisfy the condition that whenever j is outside this union, fj is 0. So we only take those functions satisfying this condition, and with this, it is very clear that the union is basically the support of the function f. And now the theorem tells you that if f is a function with period m bigger than or equals to 2 and with support s sub f of k naught, which is equals to that, the union, then for any alpha irrational number, if f is even, then this function, theta, big theta of sub f of z, or big theta sub f of alpha, is a quantum modular form of weight 3/2 on this set A sub m with respect to the subgroup gamma sub m. And when f is odd, this function, small theta sub f of alpha, is a quantum modular form of weight 1/2 on Q with respect to gamma sub m. And that basically answers question 1 and 2. So let me now give you a brief sketch of the proof of this result. Uh, so let me just give you the idea of proof. So for f even, we have to show that capital theta sub f is a quantum modular form. So what you do is you consider the Eichler integral of the small theta sub f function, where z is in the upper half plane. By that, so we denote it by theta sub f of tilde of z, which is defined to be the integral going from z to I infinity of theta sub f of tau times tau minus z bar to the power of minus 3/2 d tau. So this is basically the Eichler integral that I was talking about. So the Eichler integrals could be different in different cases, but in this case, we have to consider this Eichler integral. And one way to see what this Eichler integral is to actually take a positive integral power in the exponent of tau minus z bar. So if you take a positive integral power in the exponent of tau minus z bar, let's say k, then what this Eichler integral is telling you is that if you take the derivative of the left hand side, that means if you take the derivative of theta sub f tilde k times, you actually get back the function theta sub f of tau. So this is basically, you can think of that as the formal antiderivative of the function when k is a positive integer in the exponent of tau minus z bar. But yeah, so this is basically a generalized version of antiderivative. So now what we do is we actually use, since f is even, this function inside the integral small theta sub f of tau, it has modular transformation properties that we already saw using Shimura's transformation. And so using the modular transformation properties of small theta sub f of tau, we find some quantum modular transformation of this function, small theta sub f tilde. And then we use contour integration and asymptotics for small theta sub f of tau to find that this Eichler integral is some non-zero constant times the function which we want to show is a quantum modular form. That means capital theta sub f of alpha, and alpha is in the set A sub m. And then finally, using the last two items, you actually show that capital theta sub f is a quantum modular form. And that concludes the proof. So this is basically the rough idea of proof. For the second one, to show that small theta sub f is a quantum modular form when f is odd, what we do is we have to consider a non-holomorphic Eichler integral, which is defined in the lower half plane. So tau belongs to H minus, where tau is the set of all complex numbers with negative imaginary parts. So this time we define this non-holomorphic Eichler integral, which is defined in this way. And what you do is you use the modular transformation of this function, capital theta sub f of w. So in this case, you will have a modular transformation property for capital theta sub f of w because f is odd. And using the modular transformation property of that, you find the quantum modular transformation of this Eichler integral, theta, capital theta sub f hat function. And then you show that the Eichler integral and the function or the theta function that you want to show is a quantum modular form agree to infinite order for all rational numbers. And this is in a sense defined by Lawrence and Zagier in 1999. So what you basically show is that if you consider, so it's going to be, okay. So if you consider, let's say alpha is the rational number, then what you want to show is if you consider theta hat sub f of alpha plus it, and if you consider small theta sub f of alpha plus it, where alpha is a rational number, then you want to show that as t tends to 0, theta hat sub f of alpha plus it and small theta sub f of alpha plus it have similar asymptotic expansions as t tends to 0. So that is what is meant by agreed infinite order for all q. And this should hold true for all rational numbers alpha. And this is basically the sense defined by Lawrence and Zagier in 1999. And then using the last 2 points, we actually deduce quantum modularity of small theta sub f. And that basically concludes the proof of the theorem. Okay, let me now give you two applications of the main result that you saw in the previous slide. So we actually show the quantum modularity of the Concept-Zagier strain series, which is defined as follows: f sub t of q, which is defined by this hypergeometry expression, where these quantities h double prime t, h prime t, at, and mt are elementary explicit functions in t. I is the characteristic function here, and this square bracket is basically the q binomial coefficient, which is defined as usual. And this notation q sub n is the standard q hypergeometry notation, which is defined like this. And this function f sub t of q is actually connected to this family of torus knots. So let me tell you very briefly how this is connected to this family of torus knots. So if you take any knot k, then for this knot k, you can actually have a knot invariant, which is called the colored Jones polynomial. And in many applications, what you'd like to do is you'd like to know the cyclotomic or the non-cyclotomic expansion of the colored Jones polynomial, which is a non-trivial task to do. So this function f sub t of q is extracted from the non-cyclotomic expansion of the colored Jones polynomial corresponding to this knot, t3 comma 2 to the power of t. And this is how this function is connected to this family of torus knot. And the non-cyclotomic expansion of the colored Jones polynomial for this knot was actually obtained by Conan in 2016. All right, so another reason why this function is important to study is the fact that if you take t equals 1, then it corresponds to the function that Zagier considered in the study. So very recently, Bijavi and others established a strange identity for this function f sub t of q, similar to a strange identity for the function f of q. And they showed that this function f sub t of q satisfies this strange identity, where this equality within quotes means the same as we had before. And then in the right hand side, you have negative 1/2 times this partial Theta series, and this chi sub t of n is a periodic function. And using our result, it follows that the right-hand side, which is a partial Theta series, is a quantum modular form of weight 3/2. And from the strange identity, it also follows that this function in the left-hand side of the strange identity, f sub t of q, is a quantum modular form of weight 3/2 over this congruent subgroup with respect to the set. And then this generalizes Zagier's result, because as I told you here, that when t is equals to 1, that is equals to f of q. So this basically generalizes Zagier's result. Okay. The final application is about quantum modularity of Rogers' false theta function. So if you take any positive integer m, which is bigger than or equals to 2, and if you choose any integer j in between 1 and m minus 1, and consider this Rogers false theta function, which is denoted by f sub j comma m of z, and which is defined to be the sum running over all integers only in this residue class j mod m, and which is defined to be sine of n times q to the power of n squared divided by 2m, then and you can actually rewrite this function in this form, where the sum now runs over all integers, and then you have f of n, where f of n is defined to be a function which is 1 or minus 1 according as n is congruent to j or minus j mod m and 0 otherwise. So this is an example of an odd function, as you can see, and using our result, it follows that that this function f sub j comma m is a quantum modular form of weight 1/2 over q for gamma 7. Okay. And then more generally, you can take a positive integer in between 1 and 2m, and if you denote by f sub m of z, the following function f sub m of z is equals to the sum running over all positive integers of hn times q to the power n squared divided by 2m, where h is some odd function, some odd periodic function of period m. Then you can actually rewrite this function in this form. You can write it as a linear combination of Rogers' false theta function, and it follows that this function capital F sub m of z is a quantum modular form of weight 1/2 over q for gamma 7. So I will end my talk with these open questions. So the first is, so in 2016, Brinkman and Rowland showed that if you have a cusp form, f of q, which is defined by this Fourier expansion, and suppose this is a cusp form of weight k, where k can be any integer or half an integer, then the function f tilde of q, which is defined like that, a sub f of n times n to the power of 1 minus k times q to the power of n, is a strong quantum modular form of weight 2 minus k. And once again, when k is an integer, you can view this function f tilde of q as the antiderivative of the function f of q. And but because k is not necessarily an integer, so yeah, you can actually think of that as a generalization of antiderivative. So yeah, so Brinkman and Rowland showed that this function f tilde is an example, it's basically a strong quantum modular form of weight 2 minus k. And the question here is, develop a similar theory for any generic non-cuspidal forms f. And what we did in our work is we considered the case of non-cuspidal theta series. So the case that we considered, or the theta series that we considered, whose Eichler integral we are showing are quantum modular forms. So the theta series that we are considering might not be cusp forms. We have examples there. So yeah, so we have developed the theory of showing that this function f tilde, which are coming via Eichler integrals of theta series, which are not cuspidal, are quantum modular forms. So the question here is, develop a similar theory for any generic non-cuspidal forms f. And the second question is, are there any arithmetic properties of the coefficients of f tilde of zeta minus q as q approaches zeta, where zeta is a root of unity? When f tilde is equals to capital F, if you consider the coefficients in the q expansion of capital F of zeta minus q, then there are some nice congruence properties for this function. So when zeta is equals to 1, it corresponds to the Fishburne numbers. And Andrews and Sellers, Garvan, Straub, there are many others. Goswami and Rowland, they actually found nice congruence properties for the function of 1 minus q. And when zeta is not necessarily 1, I actually found some congruences for f of zeta minus q. And then there are also congruences for the coefficients of this function, f sub t of zeta minus q, where zeta is again a root of unity. And when zeta is equals to 1, these congruences were obtained by Bijali and others. And I obtained congruences in the general case when zeta is not necessarily 1. As q approaches zeta. So, yeah. So with that, I will conclude my talk. Thank you very much. First.
Thank you, Ankush. Any questions or queries from the speaker?
So I had one question, Ankush. First of all, very nice talk. What I wanted to know was, when you said the two functions agree to infinite order, means if you have first function evaluated at alpha plus it and the second also at alpha plus it, then as t tends to 0, both have similar asymptotic expansions or exactly the same?
Exactly. No, similar, because the thing is, the theta hat that I have defined, the Eichler integral, it is defined in the lower half plane. So basically what you actually do is you actually consider alpha minus it for theta hat, because it is in the lower half plane. And for the other function, you do alpha plus it. So there is a slight difference. But when t tends to 0, which is, or if you simply put t equals to 0, it will actually give you the same value.
Okay,
t equals to
0. At t equal to 0, they are
the same value, yeah. Because
but otherwise they have similar
asymptotic behavior, except that in the you have a power series expansion in t for both of them. And all the coefficients are same except the t. So in one of them you have it plus t to the power of something, and in the other case you have minus t to the power of something. But otherwise they are actually same. They have same coefficients in the power series expansion.
And is Bijou's paper, is it available now? I mean, is it published?
Yes, yes. It appeared in Journal of Combinatorial Theory. This is Robert's paper. Yeah.
Okay. Thanks.
Okay, any other questions or comments?
Yeah, I have a question. Yes. So in your theorem, AM is the biggest set or not?
I'm sorry.
So you have theorems. Can you change? Yeah.
Yeah, let me just.
Yeah. Sorry.
That's okay. Yes.
In your theorem, you said AM
theorem.
satisfied a modularity property, and
This one.
Yes.
Yes. Okay.
Yes, I want to ask, this AM is the biggest set or not?
No, because we're only, yeah, I cannot tell you this is the biggest set because we're only looking at cusp 0 and I infinity.
Okay.
So there
this
could
is
also be other cusps where you can find a biggest set as well.
okay. Thank you. And another question, maybe the inverse problem of this talk. So can you say every quantum modular form can be can be written in the form of partial theta series with period coefficient?
I'm sorry, every quantum modular form
can be written in the form of partial theta series with period coefficient.
Every quantum modular form. I mean, quantum. So in our case, what we showed is, so we actually showed that quantum modular forms, which are coming from Eichler integrals of theta series or partial theta series,
Yes.
are basically partial theta series, right? But you're asking the reverse question, so
yes.
I actually don't know.
Okay, thank you.
I don't think that could be the case. Maybe I'm wrong, but I think this function of Ramanujan sigma of Q, that series where Andrews, Dyson, and Hickerson, they wrote a very important paper. So that I think has Q to some quadratic power divided by 1 minus Q to the n in the denominator. So that is I think one of the prototypical examples of quantum modular forms. So maybe that couldn't be written in that form.
But that is not a partial theta series, right? It cannot be.
Yeah. I mean, yeah, I think so.
Yes. So can you prove that is not?
No. So I don't know. Yeah.
Hello, can I ask a few questions?
Yeah, sure.
So the first one is about the quantum modular form on page 15, I guess. So you list a partial theta-like series, and you claim that it is a quantum modular form. Is it in this big F sub Jm? So you claim it's a quantum modular form. Is it in the sense of taking the radial limit of Q goes to any root of unity?
Yes. So basically, this is basically an example of a strong quantum modular form.
Okay.
What we're saying is So this is the example of a strong quantum modular form, and actually, you are actually taking. So you are approaching any rational number. So this is in a sense of Zagier, which so basically he says that a function is a strong quantum modular form if it satisfies if the asymptotic expansions of that as well as the asymptotic expansions of the Eichler integrals match, right? So as tau approaches to a rational number, perpendicularly, the asymptotic expansions match. So maybe, so you're asking if this is in the sense as Q approaches xi radially. Not particularly in that sense, but the point is, you're actually approaching a rational number, one from the lower half plane, one from the upper half plane. So that is the point. Yeah. So did I stop or?
Has he got cut off? I don't know. Okay, any further questions?
Hi Ankush, Sneha here.
Hi, Sneha. How are you?
Yeah, I'm good. Sorry I missed your talk, but I hope that your talk would be available at some place. Yeah.
Yes, Sneha, I can answer that. All the talks in this seminar are being are placed on our website. I can send you a link.
Great. Okay. Thank you, Gaurav.
Yeah, sure.
Sorry, can I ask another one?
Yeah, sure.
So in the next page, you mentioned discuss form. I think it's the next slide. So in discuss form, is there any restriction on this weight K here?
No,
Does
K
it
can
has
be
to
any
be-
half integer weight. K
Can
is
be any
any
half.
integer. Yeah.
Okay. Okay, thank you. And I have one last general question. So do you expect every force or partial theta series here have an accompanying pair, which is a mod theta function on the other half plane?
That I don't know actually. Yeah. Maybe Robert can answer this. Robert, are you here?
Of course, in the literature of this three-dimensional quantum invariant of some three-dimensional manifold, there's this phenomena of this false mock pair. So we can find, so people find this quantum modular form just in between. And on one side, it's a false theta function, and on the other side, it's the mock theta function.
Yeah. What you're saying, I understand. So basically, there is a not theoretic interpretation here in the sense that if you have, so there is a duality between mock theta function and quantum modular forms, and the duality is at the roots of unity. So there is a result of Bryson, Ono, Pitman, and Rhodes, which tells you that if you that the Concept-Zagier strain series f of q matches a certain series which basically corresponds to the generating function for unimodal sequences at a root of unity. Okay? And the u function, I mean the generating function for the unimodal sequences, that corresponds to a mock modular form. And the f is an example of a quantum modular form. And the two things matches when it is a root of unity. The difficulty is actually finding these functions. So you are asking, if I have a quantum modular form here, right? What about a mock modular form different? So yeah, that's a difficult question. Yeah, I actually don't know. Yeah.
Oh, so do you at least expect this phenomenon to be very ubiquitous or not?
At least for the function f sub t of q that I actually showed, the concept is a strain series. So the point is, so the function f sub t of q that I showed in one of my slides, this is coming from the non-cyclotomic expansion of the colored Jones polynomial, right? As I told you. So if you consider the cyclotomic expansion of the colored Jones polynomial, then you can actually have a u function, and the u function is expected to have that mock modular behavior. And if you can find a u function there, then using a result of Hikami, I think you can actually find a duality between the u function and the ft function. Yeah. But in general, for any quantum modular form, whether there exists a corresponding u function, I don't know.
Okay. Okay, thank you very much.
Any further questions or comments? Okay, if not, can we thank the speaker? Please unmute yourself and just clap for a bit, I guess. Thank you, Ankush. Very nice talk. You can stop sharing if you wish.